Good morning and most welcome to 1262 of the series. It is the 20th of November. There's still no snow going about, and as you can see, we still have leaves on the bushes. Nice and warm. I will today continue with the amazing Roberto Mangabeira Unger, the cooperating partner of Smolin. We are presently at page 166. I will reread some of the page here because I'd say it's very pertinent for the lecture. The observer stands outside the configuration space. He looks upon the events from the vantage point of time-symmetric laws expressed in the timeless propositions of mathematics. The regulative ideal to which his knowledge conforms, however inadequate in a particular circumstance his fulfillment of the idea may be, is that of the knowledge that God has of the world he made. For such a scientist, past, present, and future are simply now. The Newtonian paradigm presupposes and reinforces a view of time from which physics and cosmology have never completely freed themselves in their subsequent history. According to this view, time resembles a film made of still photographs. However, time is not an accumulation of slices. Insistence on speaking as if it were a film results from the widespread antipathy to an unconditional recognition of the reality of time. The deep problem revealed in the film image of time is the difficulty that all are non-causal categorical schemes, beginning with our logical and mathematical reasoning, dealing with the temporal continuum, a subject that we address in the development of the third of our central claims about mathematics and its relation to nature and to natural science. The slice or film language is yet another way to subordinate time to the anti-temporal biases of these forms of reasoning. Indeed, this whole tradition, the commanding tradition of modern science, has trouble conceding to time the character of a continuum, not a continuum in the mathematical sense of the real number line, but a continuum in the vulgar sense of unbroken flow, not subject to analysis into discrete elements. The adherence to this tradition returns, despite themselves, to the conception of a series of still photographs. In what respect has the subsequent history of natural science reversed the implications of these ideas and practices and laid a basis for recognition of the reality of time? The answer to this question requires us to confront a paradoxical fact of immense interest to the concerns of this chapter and of this book. There is insufficient support in the dominant theories of physics since Newton's day for recognition of the radical and inclusive reality of time. The bodies of ideas that have been regularly invoked as such a foundation statistical mechanics, that is thermodynamics and hydrodynamics and quantum mechanics, fail to provide a sufficient basis. It is worth pausing to consider why, for the reasons help elucidate the enigmas that I here consider. Thermodynamics and hydrodynamics are regional theories. They address parts or regions of nature. Einstein made a similar distinction between what he called principal theories, which hold by virtue of general principles, and constructive theories, which depend on assumptions about the composition of matter. He cited thermodynamics as a prime example of a principal theory, but he would have seen hydrodynamics as a constructive theory. Such local theories foresee in the parts or regions of nature that they address processes that are in principle reversible and that become irreversible only in the context of particular initial conditions, and therefore of a particular history. Not just the history resulting from the initial conditions, but also the history resulting in the initial conditions. Despite their appeal to statistical rather than to deterministic causation, they apply only through the practice of defining initial conditions and specifying a configuration space of law-governed phenomena. For the reasons earlier adduced, this practice cannot be legitimately generalized to the explanation of the whole world. This is a rejection of the first cosmological fallacy. The attempt to ground a view of cosmic and preferred, irreversible, continuous and non-emergent time on the quantum mechanical description of the smallest present constituents of nature is misguided for a different reason. The structural outcome of a historical process, which is the subject matter of quantum mechanics, can provide fragmentary clues to the understanding of such a process, but it cannot support a general theory of the transformation that produced the outcome. Time evolution in quantum mechanics is thus reversible. It is often said that the reality or necessity of time results in quantum mechanics from the phenomenon described as the collapse of the wave function. However, such time as results from this picture of the workings of nature at a fundamental level is time in small installments. Not time as universal history. Thus, neither of the two theoretical foundations for the reality of time that the science of the last 150 years is credited with having produced, in fact, give adequate grounding for the recognition of that reality. They do not contradict such a recognition. They are consistent with it. They suggest how, once the reality of time is established on a different, more general foundation, it can be reconciled with what we have discovered to be true about the world. However, they do not and cannot accomplish the time confirming work that they are widely but mistakenly believed to perform. In the parts of contemporary science that are often alleged to provide a sufficient basis for the recognition of the reality of time, in fact fail to do so. The theories with the broadest cosmological scope have worked against such a recognition. Nowhere did this impulse to discount the reality of time take more powerful and influential form than in Einstein's physics. Under what have been its most influential interpretations. I discuss in the next section the argument in science and natural philosophy, the relation of the thesis of the inclusive reality of time to special and above all general relativity. The point of greatest tension between the argument of this book and the reigning ideas in physics. Time is absorbed into the geometry of space, captured in the idea of a space-time continuum, and made accessory to the disposition of matter and motion in the universe. Its geometrical representation provides the key to the understanding of time. The spatial metaphor describing time as the fourth dimension is the popular rendering of this explanatory move. It reveals in proto-scientific language what is at stake in this movement of ideas, the spatialization of time. In all these respects, the central tradition of physics since Newton has diminished or devalued the reality of time when it has not entirely denied it. Nevertheless, this same scientific tradition has also supported and developed the idea that the universe has a history. We know enough to assign the present universe an age of about 13 billion and 800 million years. We can infer from the study of the present universe and of the vestiges or delayed representations of the universe, what the universe at different moments in the past must have been like. We can project from our knowledge of the present and past of the universe features of its future. contemporary cosmology is almost entirely consumed by debates about this history as well as about its relation to the fundamental physical theories. How can the idea of an universal history be squared with ideas and assumptions that diminish if they do not deny the reality of time? The thesis that the universe has a history is not extraneous to the development of science. It is one of its most formidable achievements. The tension between theories or their associated explanatory practices that limit the reality of time is real. More real than we have generally been willing to allow. Draws a fault line within the established body of scientific ideas. The conception that the universe has a history, a decisive and irreversible history, is the single most important expression within those ideas of the thesis that time is real. It is therefore also the most important source of the trouble that recognition of the reality of time makes for the time devaluing traditions of science and natural history. Natural philosophy, the prosecution of an argument for the unqualified reality of time thus forces us to address confusion outside science and disharmony within it. outside science, it exposes the incoherence of some of our most influential conventional beliefs about how nature works, such as our beliefs about causality. Within science, it requires us to deal with the relation between the time-dependent idea of a universal history and foundational theories that have yet to provide a general and sufficient basis for acknowledgement of the reality of time. Put a post there. The prosecution of an argument for the unqualified reality of time thus forces us to address confusion outside science and disharmony within it. Outside science, it exposes the incoherence of some of our most influential conventional beliefs about how nature works, such as our belief of causality. Within science, it requires us to deal with the relation between the time-dependent idea of a universal history and foundational theories that have yet to provide a general and sufficient basis for acknowledgement of the reality of time. For the reality of time to be accepted without qualification, we must radically revise those conventional beliefs and distinguish between empirically validated insight and supra-empirical speculation in those foundational theories. We must accord to the idea of a universal history the prerogative that it deserves. We must consider to what extent resistance to this prerogative results from prejudice rather than from knowledge. From a certain interpretation of what science has discovered about the universe, rather than from those discoveries themselves. The argument in science and natural philosophy the conception of the inclusive reality of time and of the mutability of the laws of nature presented in this chapter and chapter 5 forms part of a larger set of ideas and arguments. I now mark out this larger terrain, later to address a particular part of it. I mark it out by emphasizing less the detailed content of the view that I here present and defend than the reasons to develop such a view. Once we place the conception in this larger context, it becomes clear that it proposes a reorientation of the agenda of cosmology, not simply a reinterpretation of prevailing scientific ideas. It rests, though for the most part indirectly, on an empirical basis. It is rich in implications that lay it open to empirical confirmation or falsification. As with any set of comprehensive ideas in science or natural philosophy, it faces the tribunal of the facts of the matter, less proposition by proposition than in the aggregate. It confronts empirical test, nonetheless, along a wide periphery of consequences and presuppositions of its tenets. In the course of developing and establishing these views, we must overcome a number of metaphysical prejudices that inhibit their understanding and acceptance. We must also distinguish in some of the most influential scientific ideas of the present. What is scientific discovery about the workings of nature, supported by observation and experiment, from what is a metaphysical gloss on these findings. This divorce between discovery and speculation is nowhere more important than with regard to the place of general relativity in cosmology. The universe has a history. Reckoning with its history is the common element in almost all important cosmological discoveries. Made over the last 100 years. Moreover, according to the view that now enjoys abundant and increasing empirical support, this history began in a supercondensed and very hot state. From that state there developed by steps the cool down universe that we observe, with its discriminate structure and its stable regularities. We know how old the universe is, or more precisely, the present universe, or its present phase, since expansion from the hot and condensed plasma that it once was. The statement that the universe is about 13.8 billion years old, now widely agreed among cosmologists, lacks meaning outside a historical account. We can, by inference from observation and theory, form a view of the early history of the universe and infer the steps by which the infant hot and condensed universe became the relatively cool and much larger universe that we observe. We can see images of its early history in the distant sky. Any cosmological or physical idea that fails to do justice to the historical character of the universe must, on the account alone, be found wanting. By this standard, empirical rather than merely speculative, the now dominant cosmological ideas are defective. So we'll continue here. We can, by inference from observation and theory, form a view of the early history of the universe and infer the steps by which the infant hot and condensed universe became the relatively cool and much larger universe that we observe. We can see images of its early history, in the distant sky. So we continue here with the lecture, and we are getting to the age of the universe. Any cosmological or physical idea that fails to do justice to the historical character of the universe must, on that account alone, be found wanting. By this standard, empirical rather than merely speculative, the now dominant cosmological ideas are defective. The discovery that the universe has a history may be thought to have little consequence for the basic ideas now ruling in cosmology and physics. At least such a conclusion may result if the history of the universe is represented as governed by changeless and timeless laws of nature, and if it leaves untouched the elementary structure of nature, as described most notably by particle physics. However, any such restraint on the implications of the historical character of the universe faces two objections, each of them developed later in this section and in this book. One objection has to do with the specific content of the history that cosmology and large-scale astronomy for close to a century have begun to disclose. The other objection goes to the idea of history. It would be a fiction to suppose that the initial conditions of the universe and the making of the basic constituents of nature before nucleosynthesis can be inferred from the now leading physical theories. At best, certain aspects of this history can be reconciled with these ideas. For example, with the string theory development of particle physics. The trouble is that these ideas, to stay with the salient example of string theory, can also be reconciled with a vast number of universes other than the one that we actually observe. It is this radical underdetermination of observation by theory that helps motivate the fabrication of imaginary universes in the multiverse conception discussed later on in chapter 3. The dominant theories break down in their application to the earliest moments in the history of the universe. A characteristic sign of this breakdown, addressed further ahead in this section, is the inference of an initial infinite singularity from the field equations of general relativity. Even on the present hegemonic theoretical ideas, it is hard to see how the laws of nature, as we now understand them, could have applied at the beginning of the present universe. One reason why it is hard is that these laws have as their central subject the interactions among the basic constituents of nature, in particular as they are represented by the standard model of particle physics. These constituents, however, including particles and fields, are themselves protagonists in this history, rather than part of an eternal backdrop to it. They emerged in the course of the historical changes in real time. It is true that computer models expressing our present understanding of the laws of nature can predict many aspects of the evolution of the universe, including its chemical evolution, converging with what we know observationally. It is undisputed that the laws, that is recurrent, formulaic, causal connections, symmetries, and dimensional or dimensionless constants of nature have been stable since early in the history of the universe. It is tempting to infer from the stability of the laws and other regularities of nature, as well as from our preconceptions about science, that the laws must be immutable. Consider, however, 4 reasons for which we should hesitate to infer the immutability of the laws of nature from their stability. A first and most important reason is that the identification of the stability of the laws with their immutability leaves not only unanswered but also unanswerable the question: where do the laws and the initial conditions of the universe come from? Historical explanation makes the question at least Vad är det som låter, Klara? Vi måste nog gå och kolla, för man har bara några minuter på sig att stänga av. Historical explanation makes the question at least in principle susceptible to an answer. It does so, however, on several provisos: that there not be an absolute beginning or a beginning out of nothing, such as implied by the idea of an infinite initial singularity; that the history be at least in principle and indirectly open to empirical investigation, if only by the traces it may leave on subsequent states of affairs, and that temporal reality or succession of universes or of states of the universe is indefinitely old, although we have reason not to conclude that it must therefore be eternal. We are unable to look into the beginning of time, that we explain the after by the before without ever reaching an initial moment is a limit to our understanding. However, it is not a circularity or a contradiction in our reasoning about what we can collectively and over time hope to discover about nature. An additional challenge to this alternative historical approach is that it is incompatible with what we call the Newtonian paradigm, with its characteristic distinction between initial condition and a bounded configuration space of law-governed phenomena. Given that here we deal with the cosmological rather than the local, we should count this incompatibility as a strength rather than as a weakness. A second reason to resist supposing that the laws of nature may be immutable because they are stable is that what we already know about the history of the universe suggests, as we later argue, that both the laws and the elementary constituents of structure of the universe must have been very different at the beginning. This inference suggests that the laws and elementary structure of nature may change, sometimes quickly and at other times slowly or not at all. A concept familiar as the punctuated equilibrium of the neo-Darwinian evolutionary theory. However, if we are to make good on the cosmological application of the idea of punctuated equilibrium, we must develop a way of thinking about how the laws and the structure co-evolve. In cosmology, there is even more reason to undertake this task than in natural history. We cannot in cosmology, as we may in natural history, reassure ourselves with the prospect that some other, more fundamental or comprehensive discipline will do the work. A third reason to avoid inferring the immutability of the laws from their stability is that among the features of the universe and of its history, there are some that are directly related to the irreversibility of the history of the universe. Prominent among these features is that the universe remains out of thermal equilibrium. We shall argue that to attribute this irreversibility either to improbable initial conditions or to a special law or principle of irreversibility is just another way of saying that explanation in cosmology must be historical before it is structural. A fourth reason not to translate the stability of the laws into their immutability is that the laws, such as we know and express them, radically underdetermine the observed universe. Computer simulations of the evolution of the universe may beguile us into thinking that after the mysterious origins, everything else is accounted for by the established understanding of the laws of nature. In fact, there is no such gapless synthesis of the now standard cosmological model and of the standard model of particle physics. Particle physics accommodates our universe only by also accommodating countless other universes. In the existence of which we have no other grounds for belief. The reasons to think that the historical character of the universe may have far-reaching consequences for cosmology are not limited to the implications of this history for the premise of the immutability of the laws of the universe. They have to do as well with the idea of history, with what the claim that the universe is historical means. If history were determined by structure rather than the other way around, and if the determination of history by structure were expressed by eternal laws of nature the result would be to eviscerate the sense in which there is history at all. Laplacian determinism and its yet more radical successor, the block universe understanding of the cosmological implications of general relativity, and now the significance of time. They place the end in the beginning. That is not history. It is the negation of history. Its opposition to history ends in a denial of the reality of time. It places the scientists in the position of God in the Semitic monotheisms, for whom there is only an eternal now, because he sees the end in the beginning. It is a problem familiar, at least for the last 150 years, to students of human history and of social theory. Belief in the existence of permanent laws governing the succession of institutional and ideological regimes in the history of humanity was justified, among other ways, by the claim that without such belief, historical explanation would be left with no basis whatsoever and descend into a narrative agnosticism. Yet the loss of that faith has been followed by new forms of causal explanation, dispensing with the notion of timeless laws of historical change. So it must be and can be in cosmology. The question then arises whether any aspect of nature is exempt from this history. That is to say, from susceptibility to change. Under the views that have long been dominant, much of fundamental importance is exempt from change, and in this sense is unhistorical. What is most unequivocally left out of the history of the universe are the laws, symmetries, and supposed constants of nature. These regularities, according to long and widely held conviction, from which only a few scientists have dissented, are unchanging. Indeed, many philosophers and scientists have mistakenly regarded the idea that all the laws, symmetries, and constants of nature may change as nonsensical. Also left out of openness to change, according to the prevailing views, is the elementary structure of nature. These exemptions from the reach of history and of change are so entrenched in established scientific thinking that they have survived successive revolutions in cosmological and physical theory. The assumptions underlying them have set their mark even on theories that put the idea of succession of universes in place of the idea of a plurality. Such cyclic universes, for example, now in the early 21st century, those of Penrose and of Turok, commonly suppose that the successive universes exhibit the same structure and conform to the same laws. These prevailing ideas about the distinction between that what changes and what fails to change in the history of the universe have a twofold basis. One basis is the stability of the laws, symmetries, and constants in the observed cool-down universe. From stability, it is common to infer immutability. Whether this inference is justified, however, depends on the facts of the matter about the history of the universe. The current cosmological models imply that the universe may in some states exist in a condition of extreme density and temperature. These states may be incompatible even with the elementary structure described by the standard model of particle physics. They may fail to conform to the regularities, laws, symmetries, and constants found in the cooled down universe. In other states, however, nature exhibits a structure and appears to obey such regularities. To regard these law-obeying and structurally differentiated natural states as the sole regime of nature, which is the second cosmological fallacy, is then to misrepresent the universe and its history. The stability of the laws, symmetries, and constants of the nature finds its most ready explanation in these historical facts about nature rather than in the speculative idea of unchanging laws, symmetries, and constants. Another source of the unjustified inference of the immutability of the laws and symmetries and constants from their stability is a pair of notions at once methodological and metaphysical. According to one of these notions, the idea of changing laws is confused, self-defeating, or senseless. We can discern change only by reference to something that does not change. It is on this view only because part of nature, including its basic structure and laws, fails to change that we can hope to understand the part that changes. This objection, however, would count only against the view that all laws change at once or in the same way. Nothing about nature or its history suggests that laws could change in such a fashion, if indeed they do change. This false objection is, however, related to the real problem. The one that we address in this book under the label of the conundrum of the meta-laws. The second methodological and metaphysical notion deployed in the attempt to infer immutability from stability is the claim made by Poincaré and many others that science cannot dispense with immutable laws. This objection, however, amounts to an attempt to entrench a particular explanatory practice as a requirement of science. It is contradicted by the methods of the life and earth sciences, as well as by those of social and historical studies. The conundrum of the meta-laws suggests one of several reasons for resistance to the idea that the laws and other regularities of nature may change. The idea that the laws may change, notwithstanding their stability in the cool-down universe, seems to present us with an unacceptable choice between saying that such change is law-governed, with the result that the high order or fundamental laws then benefit from an exemption from history that we deny to the lower order or effective laws, saying that the change is uncaused, with the implication that it is arbitrary or uncertain in reality, not merely unknown to us. The view that the universe has a history, amplified by the conjecture that everything in the universe, including its rudimentary structure and its laws, changes sooner or later, and has indeed already changed in the past, can be stated radically and comprehensively only if we accept that there is a preferred cosmic or global time. Very good here. A simple description of what such time means is that everything that has happened or that will ever happen in the history of this universe or in the history of the universes that may have preceded the present universe can in principle be placed on a single timeline. When I subsequently use the term cosmic or global time without further qualification, I mean it in this sense as a preferred cosmic time. That is incredibly interesting. Without a strong, non-arbitrary conception of preferred cosmic time, the reality of time and the historical character of the universe would be limited and compromised for reasons that each of us later discusses in greater detail. Take reasons. These reasons can be summarized as follows. First, if there is no cosmic time, then there can be no overall history of the universe, only a series of local or fragmentary histories. Such histories are history in a diminished sense. They treat history as subordinate to structure. Structure or structural explanation may be first, if there is no cosmic time, there can be no overall history of the universe, only a series of local and fragmentary histories. I think that's important to remember. There is a demand here for a time that is eternal. It is very, it's a necessitated establishment. Yes, necessitated establishment. Second, if there is no global time, the non-existence of such time in the mature universe must relate to events in the very early universe in one of two ways, either of which is troubling. In one view, there may have been a unified time at the very beginning, when the universe remained super hot and super condensed plasma, within which light was trapped rather than a gas within which light could travel freely. Then, however, as the universe began to expand, there ceased to be a time common to events in the history, common to events in the universe. It then seems that the disintegration of time is an event within a larger history, rather than a deep feature of time. On another view, cosmic time never existed, even at the beginning. If so, it becomes unclear in what sense we can say that the present universe has a history at all, or make empirically grounded claims about its age, it becomes senseless to state, as cosmologists now generally do, that it is about 13.8 billion years old. Third, if the reason for the non-existence of a preferred time is the inseparability of time from space, or more specifically, its shaping by the geometry of space and the disposition of matter in the universe, as the leading interpretations of general relativity imply, then the non-existence of global time results in a substantial qualification to the reality of time altogether. The combined and cumulative significance of these considerations is to suggest that we cannot rid ourselves of cosmic time without at least diminishing the sense in which time is real at all, as well as the sense is in which the universe has a history. Any discoveries about the incidents of this history may require more or less radical reinterpretation if they are to be reconciled with a theoretical denial of a unified time expressed in a unified history. The end of cosmic time as a legitimate, factually based, scientific concept represents the beginning of the end of time itself. The existence of a preferred cosmic time seems to conflict with general relativity. The ample empirical and experimental support for general relativity may therefore appear to strike a fatal blow against the idea of such a preferred time. I discuss this apparent contradiction in two steps. First, here as a part of the development of the idea, and then later in this section with emphasis on the implications of my argument for the future agenda of cosmology. In general relativity, the relativity of simultaneity is enlarged into a general freedom to choose the time coordinates on the space-time manifold. From the standpoint of the theory, such a choice is arbitrary. There are many cosmic timelines, not one, in that strong sense, of one preferred cosmic time. There can be no preferred time, no one timeline describing exclusively the history of the universe. The non-preferred time suggested by the relativistic way of thinking is a feature of its way of representing the universe, not just a contingent aspect of some classes of solutions to its field equations. It is incidental to our arbitrary slicing of the space-time continuum, described as a four-dimensional semi-Riemannian manifold. Under the aegis of this idea, we can always slice the cosmological solutions of general relativity into an evolving succession of space-time states. Almost every cosmological solution under the leading interpretations of general relativity into an evolving succession of space-time states. Almost every cosmological solution under the leading interpretations of general relativity can be represented as one parameter succession of states. It must conform to the assumption of a gauge invariance, rendering the choice among such representations devoid of physical significance. Moreover, we can slice the space-time continuum in a mathematically infinite number of ways. A defender of this eviscerated view of global time against any proposal of a preferred cosmic time may object that whereas the former benefits from the ample empirical support for special and general relativity, the latter requires a conjecture for which there is no corresponding validation. This objection amounts to an illegitimate shifting of the burden of proof in the debates needed to illuminate the future path of cosmology. Neither relativistic time, understood in the now traditional way, and therefore subject to arbitrarily chosen space-time coordinates, nor a preferred cosmic time, is directly observable. Nevertheless, the latter may figure as the former already does in theories generating a host of implications susceptible to empirical confirmation or challenge, as well as to experimental inquiry. The question is, which of the conflicting bodies of ideas taken as a whole generate the most fertile research